This lecture continues the previous video where I would describe uniform circular motion and the velocity selector. In this video, I'm going to describe a third situation, right? A physical situation that involves a magnetic field. And this one is really interesting. Not that the other two were not interesting, but yeah, this is called the Hall effect. It's named after a person whose name is Hall. So the idea is you have a magnetic field, right? So I've drawn a bunch of magnetic field lines, and you can see that I tried to indicate a uniform magnetic field, although the truth is it's not that important. But it is important that the magnetic field points basically only in one direction. So I've set it up so the magnetic field is pointing towards you, right, coming out of your screen. I've also drawn this sort of messy gray thing is a short section of an electric wire. And that wire is carrying a current I, right? So, and I'm talking in terms of the conventional current. The current is flowing towards the right, and I describes a certain amount of charge per time that flows towards the right. Okay, so the Hall effect is associated with this particular setup. I've got a current carrying wire immersed in a background magnetic field. So let me describe that. Current carrying wire immersed. That is, the wire runs through a space that is full of magnetic field in a background. Magnetic field. Okay, so we know electrons are the charge that flows as current on wires, right? And the reason that we know it actually, or one of the ways that we can be confident that is the case, is because of the Hall effect. What we do is we pay attention to a particular effect. So let me redraw this situation, but I'm going to indicate the electrons that are the objects that are moving as the current, and also the background nucleuses. Those are the positive charges that do not get to move. All right, so let's see what happens. So here is the magnetic field, and let me draw us a wire. All right, and in this wire, I'm going to indicate with little blue positive signs. There are these positive charges that do not get to move, right? They're the nucleuses. They are the wire, essentially. And with little minus signs, I'm going to indicate, right? So every plus has a minus because this wire is not electrically charged, although there is electric charge in it, right? And these little negative charges are actually moving towards the left, right? So I'll just draw a few of them. Okay, so those electrons are moving towards the left because remember that the conventional current is the direction of positive charge flow. So if you think about which direction positive charge flows, well, if negative flows to the left, that's the same thing as plus flowing to the right. But we know that they're flowing leftward, right? Because we know electrons are the charge that flows as current on wires. But remember, there's this background magnetic field. And the force on the little negative charges is equal to, so they are each little negative e's of charge. So Q, V, cross B, right? So these are the forces on the negative charges. So the magnetic field is outwards. So V cross B is actually, if you use the right hand rule, once again, I'll warn you, if you don't know what I'm talking about or you don't know how to use this, you're missing the point. You should push pause and go learn how to use the right-hand rule. I've said it a few times. I hope that at some point, if you haven't taken me seriously yet, you're beginning to take me seriously and you actually follow through. You're doing yourself a disservice if you're skipping this, because you're going to miss out on how to do this physics. So according to the right-hand rule, V cross B is actually up. But because of this minus sign right here, the opposite of up is down. So the force on the negative charges is actually downwards. So each of these little negative charges, as it flows towards the left, it's tugged down, right? All the little electrons, as they flow to the left, are tugged downwards. So what this means is that this wire gets negatively charged along the bottom, right? The negative charge is moving to the left, and what's left over at the top is positive charge. That is, the wire is polarized, and the bottom of the wire is negatively charged, and the top of the wire is positively charged. There's definitely a current flowing. That's not changing, but the wire is actually charge separated. And this charge separation is associated with an electric field. Actually, let me draw it in red, say. No. Well, yeah, I think you know what I'm saying. There's a background magnetic field pointing out of the screen, and because of the Hall effect, right, this is the Hall effect, there is electric field that builds up. And remember that electric field points from high voltage to low voltage. That is, the upper side of the wire is at a higher potential than the lower side. And you can use a voltmeter to measure this Hall voltage. So this is based on our assumed knowledge that the electrons are the type of charge that flow in wires. But let's do the opposite assumption. Let's make an assumption that instead, if I have a current flowing to the right, then what that means is I have a bunch of stationary electrons. So let me draw these electrons. I'm going to imagine that they actually don't move. And instead, I've got positive charges that flow. And this is the current. So remember, the magnetic field in the background is out of the page or out of the screen. So if you do V cross B itself, right, is down. And because the charge that's moving, right, the Q is positive, the magnetic force is positive. That is, the positive charges are forced downwards as well. Can you see that the B field is the same in my electron flowing assumption as it is in my proton flowing assumption? The magnetic field's in the same direction. The current's in the same direction. But the charge that I assume to be moving is the positive charge, and you can see that it is pressed downwards. What's interesting is that's the same direction that the electrons were pressed. So the electrons were pressed down, which caused a negative charge on the bottom and a positive charge on the top. But now in this assumed scenario, what I get instead is the positive charge is pressed downwards. And the negative charge is what's left over at the top, which means I have a different kind of electric field. It's an electric field that actually points upwards instead. And the high potential is on the bottom instead, and the low potential is on the top. It gives me the reverse. So you can measure, although it's actually quite tough, the voltages are very, very small. These Hall voltages, right? The Hall effect voltage is very small, but you can measure the Hall voltage. It will be small, but you can tell the difference between being high on the bottom and low on the top, or low on the bottom and high on the top. Yeah, so this is the Hall effect.